So no matter, we can solve this also. So what you have here, that you have a reservoir uh, in a point A where water is filled. So this is water is at 20 degrees C is to be pumped from a reservoir ZA equal to, so the depth here is 5 meter, to another reservoir at a higher elevation where ZB is equal to 13 meter, through a 36-meter long pipe connected in parallel. So this is one pipe which is length is 36 meter. This is the another pipe which is also a length of 36 meter. Uh, now these pipes have two different diameters, 4 centimeters and 8 centimeters. Water is to be pumped by a 30% efficient motor pump combination. Means it is combined efficiency of motor and pump, not only motor. It is the efficiency of entire combinations, which consumes electricity of 8 kilowatt during the operations. Minor losses and head losses in the pipe that are connected in parallel to the reservoir as considered to be negligible. It means whatever the losses, minor and major, both losses are the negligible for the time being. Determine the total flow rate between the reservoirs through each of the parallel pipes. Means you are supposed to calculate how much flow rate is going into the pipeline 1, how much flow rate is going into the pipeline 2. Is the problem clear?
Yes, sir.
Right? So from point
Yes,
A,
sir.
you are moving to flow to point B. And there are the two pipelines. Length of each pipeline is same, only diameter is getting changed. And here you are having a pump connected to that. And you are supposed to calculate how much flow is going to this, how much flow is going to second pipeline. So first part, you will always apply your energy equation between point A and point B. Now to reach the point B, you have two different routes. One route is there by following point A, you can follow path 1, you can reach to the point B, or from A you can follow a path B, you can path 2 actually, you can reach to the point B. Both the way you can reach to the point B. So we can apply energy balance between point A and point B. So that's what I did here. So applying energy balance between point A and point B. So this is pressure and point B divided by the rho g alpha A B A square upon 2G ZA. In between of that you have a pump. So this is the head delivered by the pump HP, point B pressure and velocity and Z and a loss here. This is the loss, all the losses between point A and point B. So if you want to go via a point B, point actually pipe A means for pipe number 1. Same thing you can reach also pipe number 2 also. So left hand side would be same, only right hand side getting changed. Here you are putting all properties of your pipe B, correct? Hello? Right? So now in this case, what you have here, both the tanks you see uh, open to atmosphere. So pressure at point A, PA equal to PB equal to P atmosphere. And if you want to write in terms of gauge, that would be equal to 0. So that's what I wrote here. PA equal to PB equal to P atmosphere equal to 0 in terms of gauge pressure. Considering turbulent flow, your kinetic energy correction factor alpha A and alpha B are considered to be 1, because as we have proved in previous classes, for highly turbulent flow it comes to 0.01. So we are considering it 1, and all the time we consider is 1 for ease of calculations. then both the tanks are open, and then we are considering it also a large reservoir. We are considering a large, these are the assumption from our side. So velocity of point A and point B is also equal to nearly zero actually. So BA equal to BB and the free surface of velocity, which is also equal to zero actually. Okay. So by putting all these things here, so this equation, either first one or second one, you can end up with this. Your ZA is 5, HP you need to calculate, and you have here ZB is 13. F1 you don't know what is the friction factor value actually, and L upon D you already know, V square upon 2G, because you need to calculate what should be the flow rate, correct? So these are the unknowns you have. Is this fine till here?
Yes, sir.
Yes, sir.
So can you able to do till here, till this particular point?
Yes, sir.
Sir, alpha A, alpha B equal to 1.
Yeah, alpha A, alpha B, these are the kinetic energy correction factor, and for turbulent flow, these comes equal to 1.
Okay, sir.
So now you have here F is friction factor. So friction factor in this question is not given to you. So that is the missing part here. So for time being, the friction factor in pipeline is given 0.01. So F1 is given to you, that you can note somewhere. That is a friction factor 0.001. It is being considered that much. It's given in the question actually. I
But sir,
forgot to type.
excuse me, sir.
Yeah.
Sir, in the question it is written that minor loss and head loss in the pipe are should be neglected. I think there is somewhere written in the question.
Let me see. So minor losses and head losses in the pipe that are connected in the connected to the parallel. It means that these are the parallel pipeline from this is the point here joining. This is the point. This is
Okay,
the
sir.
joining till here. This point. This is the
Hmm.
point joining here. This. So your parallel loop ends only in this particular loop. This is the rectangle. So your pipe which is connected to this here, this end, sorry, this is connected to this end, and this pipe connected. So these are the connections. For these, the losses are not being considered. At the same time, you have a T here. For that also the loss is not connected. A band here which is also not considered, which is here. All sort of fittings. We are all the, and these all pipes. For that the losses are not considered. However, this
Okay, sir.
side the losses would be considered. This loss would be considered. Okay.
Okay, sir. Okay, sir. That is
Okay.
why that we are calculating that F1 thing using we are using the F1 thing.
Yeah. So you have this. So for that case, this is the relationship you will get, because here you know the
Yes, sir.
F1
Yes.
I gave you just now 0.001. L and D is given to you. D is given for D1 is 4 centimeter. You have converted into the meter. Okay.
Okay, sir.
So it is fine for everyone. Please make sure this is the way only all problems would be solved. So if you understand one, you can do any problem actually. Because in all other problem, only thing with variation would be this F. Here I gave you F. Somewhere you have to calculate the F only. So this is one. Now what else is given? For parallel connection, you know this thing, right? Parallel connection, the head loss in pipe 1 would be equal to head loss in pipe 2.
Two. Yes.
So this is the from parallel connections of the pipe. So you can write also the same thing, substitute the values for all of them. So you will get V2 would be equal to under root of 2 of V1. Do it same time with me only. So you got this B2 equal to root 2 of B1.
Yes, sir.
Hello? Okay. After that, whatever flow is coming from here by this pump, it getting divided into two parts. One is will go pipe 1, other will go to pipe 1. So your total Q would be Q1 plus Q2, right?
Yes, sir.
So that we want to do now from continuity, which is your mass balance. Because if you will put the density both the sides, you will get the continuity. So in this case, your A1 B1 of pipe 1, A2 B2 of pipe 2, add them up, you will get the total flow rate coming out from the pump. Now you are converting everything B2 also in terms of V1. So if you will substitute your B2 expression in terms of B1 here, so you will get this relationship here. So this would be this one actually. Are you getting this B1 equal to 103.88 Q? आया किसी का?
Yes, sir.
Okay. Go back. There was the correction here. Now, once you got this, now you go back your HP equation. This is your HP equations. Head of the pump is 8 plus 5 upon 109 B1 square. Now you know your HP is this. V1 you got this 103.88 Q. So you have put here. So from here you are getting HP in terms of Q, right? This is what you got. Fine.
Yes, sir.
Now आपके क्वेश्चन में क्या दिया है? The power of this pump motor combinations is कितना पावर कंज्यूम कर रहा है ये? 8 किलोवाट, right? So
Yes,
in
sir.
your question it is giving 8 kilowatt. So from there if you want to calculate head of the pump, so head of the pump would be the power consumed by the pump divided by Q rho G. Q is the flow rate, rho is the density, and G is the G. So from here you can calculate what should be the head of the pump. So power of the pump consume 8 kilowatt. Means the efficiency was given to you the 70%. So the 70% of actual power consumed would be delivered to the fluid actually. So from here, this is the actual power that delivered to the fluid divided by Q rho G. So you will calculate the HP. So write this equation HP equal to power upon Q rho G. You know the power, you know the efficiency 0.7. Q is unknown. Rho is density of water is 1000, G is 9.81. So you will get this is HP equation. You already know one HP equation is this 8 plus 5 by 109 103.88 Q square. So you have two equations for HP, equate them, so you will get this equation, this one. Okay. तो पावर
Sir,
ऑफ
ये
द फॉर्मूला इज 2H rho G. हाँ बोलिए.
सर ये एचपी का फॉर्मूला पावर अपॉन कैसे आया?
देखिए, पावर ऑफ द पंप फार्मूला इज क्यू एच रो जी. दिस इज द पावर ऑफ द पंप. इस प्रैक्टिकली यू पंप क्या कर रहा है? पंप आपका फ्लूइड को एक बॉटम से इज मूविंग एट टॉप, राइट? करेक्ट और नॉट? एलिवेशन चेंज कर रहा है ना पंप ओनली,
यस सर।
करेक्ट? सो एलिवेशन चेंज करके यू आर चेंजिंग द पोटेंशियल एनर्जी ऑफ द फ्लूइड. पोटेंशियल एनर्जी का फॉर्मूला क्या है?
रो जी एच।
mgh, right? Potential energy formula is mgh. How would you calculate mass, volume into
डेंसिटी।
Density.
density? Now, volume into density is mass, so mgh would be energy. So if you want to calculate energy per unit rate, so you will need a mass flow rate. So q into rho would become mass flow rate only. So this will become a rate of energy, that is called power only, correct?
Correct, sir.
ठीक है ना? So from there, power of the pump formula is QH rho G, where H is height or head given by the pump, Q is the volumetric flow rate, rho is density, G is G only, right? So from there only we are calculating what should be the head given by the pump. Okay?
Okay, sir.
So from here you got another equation for HP. This is 0.7. This is power consumed 8 kilowatt. Q you have to calculate. Density you know 1000 and G is no. This is one formula for HP by doing head balance. From the previous part, that means the energy balance. Equate the two, you will get this equation. And finally, if you will solve it, you will get in this particular format 495.0799 Q cube plus 8q minus 0.5708. So this is a quadratic equation, third order cubing equation actually, sorry. So you can solve it by finding a root either by trial and error or some other technique. So if you solve it, you will get q is 0.058781. Okay. In your calculator, you have some inbuilt functions also, which may find this root also, cubic equation. नहीं है तो root find out करने के लिए there are some methods are being taught to you in your mathematics and numerical methods. Hello.
यस सर हो जाएगा।
So this q can be
Yes, sir.
calculated. Once
Yes,
you
sir.
got the q, you know the q ही calculate करना था, right? So you got the total flow rate. From here you can calculate how much is V1. So you already have the expression for V1 103.88 into Q. So you got V1. Now once you know the V1, you can calculate your V2. So you calculate V2, you can calculate the ratio of Q1 upon Q2 by this only A1 B1 upon A2 B2. So you can find the ratios, what ratio is flow rate is being the divided only. So this way, this particular problem is complete, which is of parallel pipeline, without considering any minor in the losses. Does anyone have any doubt in this? पहले आपने यूज किया एनर्जी बैलेंस, आफ्टर दैट you did the head balance in parallel connections because the head loss in all pipes should be equal. Then you have used continuity. After that, whatever you got one head equation from the power consumed, and you have equated the two and you have solved the rest of the things. This would be used in almost all questions. That is the procedure. Okay.
Yes, sir.
Now, this is the another question. This is one way that you just maybe you can take a picture of that, or I will send those means complete the slide to you. This is what a completely a gravity flow here. ये tank आपका एक now a higher end. Now from here fluid is going to a lower end. Here you have all fittings. सारी fittings आपको दिया है, सबका नाम भी जहाँ लिखा हुआ है. At this age, they have mentioned sharp edge entrance. For that, loss coefficient is given KL 0.5. This is a standard elbow, 90-degree elbow here. So for that, the loss coefficient is standard elbow flange type. So for that, KL is given to you 0.5. So for this also KL 0.5. This also KL is 0.5. There is the gate wall. For that, the loss coefficient fully open conditions is KL value is given to you 0.2. This is your sharp exit end. So exit losses we mentioned all the time. For all type of the exit losses, the KL is 1 actually. So they have given value is 1.06, so nearly 1. So for this also you have here 0.1 Z1, 0.2 here Z2. You have to again use same energy balance between 0.1 and 0.2. So you have P1 upon the rho g alpha 1 B1 square upon 2g plus Z1. In this case, you don't have pump, so you don't have to add HP term. Now, this side would come your P2 upon the rho g B2 square upon 2g plus Z2 plus all head losses, right? And here you will have all head losses, your minor losses, your major losses. You see here, these are the data given to you. Viscosity of the fluid, which is water, is given to you 1.307 into 10 to the power minus 3 kg per meter second or Pascal second. Density is 999.7, so you can take thousands also, that's same thing. And roughness is also given because this pipeline which is made up of that, this is made up of cast iron. For that, the roughness is given to you 0.00026 meter. So आपको सब कुछ दिया है. And flow rate is also given. How much flow rate is going on? 6 liter per second. Diameter is also given is 5 centimeter. Okay. Now, procedure is same for this also. You apply energy equation at 0.1 and 0.2. Same consideration here because both the tanks are open now. So P1 actually practically P1 here. P1, P2 equal to P atmosphere equal to 0 in terms of gauge. Kinetic energy correction factors, we are always considering 1, considering the turbulent flow. BA equal to BB means that is also equal to 0, the free surface of the large tank. So these are all the time is consideration in case of open surfaces actually. These three considerations are always true. Second is always true, kinetic energy correction, we are taking always 1 because all real flows are the turbulent flows only. So if you will substitute that thing here, so you will get Z1. Now this term will Z2 you know is 4. Can you see from the here Z2 is 4 or not? Z1 कितना है?
Z1 calculate करना है.
हाँ? Z1 calculate करना, we
Given
don't know.
Z.
Z2 is given to you is 4, right? So Z2 is 4. In between of that, आप देखिए क्या क्या दिया है. यहाँ से यहाँ तक from here, this is the pipe, one pipe. This is another pipe from here. After that, another pipe. So you have pipe this length. ये length कितना दिया है pipe का? You see from here to here. कितना मीटर है length?
80 मीटर.
80 मीटर तो ये लेंथ हुआ. So it means this include this length and this length. But ये भी length है, right? This is also the length of the pipe. 9 meter. The total length of the straight pipe length is 89 meter. Correct? So that's what you have here at this place. Your L is 89. So you have here the straight pipe loss. Now you see the fittings. Kitna fittings hai yahan pe? One fitting is here, sharp edge entrance. So for that I wrote here K entrance losses B square upon 2G. This is the losses by sharp entrance. Now how many elbow? One elbow here, one elbow here, two elbows, right? साथ में बोलते
Yes,
रहिए,
sir.
right? So two elbows. So I multiplied here
Yes,
by
sir.
2 K elbow, the loss coefficient of the elbow V square upon 2G. एक इसमें valve दिया है, right? There the one gate valve fully open. So you have that also K valve V square upon 2G. उसके बाद there is the exit loss also here. That is the also given one exit here. So for that also I wrote here K exit V square upon 2G. और कोई इसमें component नहीं है, right? There is the no other component here. Correct or not?
Yes, sir.
बाई चांस एक पंप होता है तो आप पंप को इस साइड में ऐड करते हैं, जो है लेफ्ट हैंड साइड में. यू कैन ऐड ए टर्म हियर HP if pump is there, but pump is not there, so that component has not come. Fine.
Yes, sir.
Now we have to substitute all those. So we know the flow rate, we can calculate velocity. Q is given the 6 liter per second, right? So लीटर को मीटर क्यूब में कन्वर्ट कर दीजिए. सो 1 liter equal to 10 to the power minus 3 meter cube. So you will get this, and you have the cross section. So divided by area, you will get the velocity 3.045 meter per second. Okay.
Yes, sir.
You will get velocity. After that, you calculate the Reynolds number, RE, which is your dB rho by mu. So you put the value of your diameter, velocity आपने just calculate किया है, density you know 1000, viscosity is given to you 1.307 into 10 to the power minus 3. Substitute this here, you are getting dense. This is the Reynolds number 35 lakh something. 35,69,333 something. Can I move just a bit faster? So because I have to start one more session of the course. So you will get this RE.
Yes, sir.
Yes, sir.
Once you will get this RE, now this is the formula in Holland correlation, which I actually told to you. This would be given to you actually. So this is the formula when the RE value is more than 2300, just to calculate the friction factor. Roughness दिया है आपको in the question, right? Roughness is given, diameter is given, RE you have calculated just now. Substitute everything into this equation. You will get your friction factor from here. F is 0.03158. Okay.
Yes, sir.
So once you calculate F, now you go back to your this equation, because here only unknown was F only. F was unknown and Z1 was the unknown. So you have known this known. Now right hand side completely known. So you can calculate your Z1 now. Correct? So from
Correct,
the
sir.
equation 1, substitute all these values, because B square upon 2G was common everywhere. So I took the common here. Then you just substitute everything here. You will get your Z1 equal to 31.8571 meter. So that's complete your entire problem. So we did two problems. One is in parallel, one is in the series combination with all fittings, with all type of the losses, and this complete your practically your all pipe losses calculation, pipe fitting calculation type of the questions. So just go through that, try to solve it your own. If you don't get it, any doubt, you can call me anytime. So with this, we will end here today. Okay. These slides, I will send it to you on your Google Classroom today only. Fine.
Thank you.
Okay, sir.
Yeah. So thank you very much, and just try to manage some extra time for class so that I can explain you some more problems where you need some other things, other complicated type of case study at least. So these are the typical one. Most probably use this one only.